there are course announcements. Your homework is due this coming Wednesday. I think I may have to move my office hours, and if I do, I'll extend the homework. It's an if. So remind me at the end of class, and I'll double check. I just noticed something on the way here. I spoke to my phone. Right. Other than that, again, your project proposals are due soon, and you have a quiz due roughly at the same time. That's my bad. Any questions about procedural stuff? This class is pretty easy organizationally. Cool. So today we're going to talk about texture mapping and a tiny bit about shaders. These are topics that I love, and so there's that. Yeah. So let's talk about texture mapping and shaders. So we ended the lecture last time with these two images, right? This is Agent whatever the heck from Star Wars. What is his name? What is this movie? The Matrix, Agent something? Orange? I don't know. This is some movie character, and one of these is real, and one of them is fake in every pair. I honestly forgot to look up which one is which illustrates my point, which is that it's hard to tell the difference. And of course, the reality here is that shading models are a heck of a lot more complicated than the teapots we showed in our last lecture. And they involve things like not just anisotropy, but also textures that vary along a surface, different materials, and so on, right? And that's what makes a scene look interesting. And so our goal today is to talk specifically about spatially varying texture and material, right? And so far, all we've done is like render these like nice golden shiny teapot things, but the reality is we want things like leopards or cheetahs or whatever this thing is. I'm off to a rough start today. Where different parts of your surface have different materials. And essentially the calculation is not so bad, right? And what we're going to do is run our ray tracer, figure out what point the ray runs into, and then do a calculation to ask what is the material at that point, and then use the stuff from the last lecture. Right? And so the difference from the last lecture, before the material was the same, now it varies depending on where you are. Cool? Alright, so another way of thinking about that is we're going to allow the parameters of your to vary spatially, and that can make some pretty complex appearance using some pretty simple algorithms. And I think something that a lot of intro graphics classes kind of skip over is they talk about texture mapping, and then they talk about BRDFs. And they think about texture mapping as just like kind of gift wrapping a color onto the side of the surface. But the reality is texture mapping can be used to make spatially varying anything, not just diffuse color, but the specular highlights, whatever. And that really can create some interesting effects without any additional CPU work. Okay, so that's what we're going to be up to today. And there's two kind of big approaches here. One is to do this from data. This is called texture mapping. So we're going to spend the majority of today's lecture. Notice that we're going to slowly start transitioning from ray tracing to more kind of hardware-based things. So the first approach is texture mapping, where essentially what we're going to do is store some photograph or JPEG underneath, which is going to keep track of the texture. And when we intersect a ray with our object, we're going to look into this image to figure out the color that I should have at a point. That'll be approach number one. And the reason why we do that is, remember that typically the triangle meshes that we've encountered in this class are pretty sparse, right? Like the triangles, you can see them on your computer screen. They're bigger than a pixel, right? And so this is essentially storing the sub-pixel data, which accompanies the kind of sparse piece of geometry, rather than just having a gajillion triangles, which are pretty hard to deal with because it's kind of unstructured data. And then the other thing we'll talk about at the very end of class, depending on timing, is something called a shader, which is like a little program that computes your shade as a function of where you are and your camera parameters and all that kind of stuff. And later on, when we talk about how OpenGL is structured, we're going to see that shader is kind of the primary component that goes into writing graphics card code. But the reality is actually, if you look at the history of shaders, they originally kind of come from the ray tracing world. That in fact, I think the very first shaders appeared in RenderMan, which is sort of a movie industry style rendering package. And the basic idea of a shader is that it's just like that little function in your ray tracer which takes in all the information about your scene and outputs a color. That thing you could think of like a shader, and people develop special programming languages just for writing those, because there are certain patterns that kind of appear and reappear in that world. Okay, so for now we're going to talk about texturing, and texturing is a topic that's very close to my heart, and I'll show you why in a little bit. But the basic idea here is that typically your 3D models look something like this rhino on the left-hand side, right? There you can see all of the elements, the quads in this case. It's a very nice quad mesh, by the way. So if we just use our contents of our last lecture, it looks like a rhino, but it looks like a pretty boring, smooth rhino, right? And so at the end of the day, what we're going to do is say, well, if we have this guy and a picture of a rhino, how can we put these things together to make a nice 3D object where we can kind of incorporate information from the photograph but still change the camera angle? Right? That's our basic task. And of course, this is something that's been around for a long time, and more or less, it just looks like this, right? That we're going to kind of think about just like putting up wallpaper with dollar signs because you're engineers and you make a profit, I guess. There's a big argument about this in today's faculty lunch, and I'm still all hot and bothered about it. But that aside, right. The basic idea here is that the wallpaper is going to be like some image that I'm going to store on the pixel grid. And the work that we're going to have to do in texture mapping is wallpapering this thing onto a 3D shape. You know? And of course, that's a challenging problem if you think about it, right? Because 3D shapes aren't flat, they're not developable, which means that when I put that wallpaper on the shape, necessarily I'm going to introduce some distortion, right? And so accounting for that in a clever way is a topic that people still think about today, right? In fact, if you look in the art pipeline, both in video games and in movies, you'll see that there's a lot of people whose job, they call it like UV mapping. And essentially those people's job is to figure out what pixels in the image grid correspond to what points on a 3D surface. It's kind of amazing that in 2018, we still have people whose full-time job it is to like try and solve by hand some geometry problem, but that's kind of where we're at right now. So for most of today's lecture, we're going to talk about, once you're given a texture map, how to render with it. An additional topic that we'll just barely touch is how to actually find the texture map, which is a fun, tricky thing. Okay? And so at the end of the day, you know, our goal is to take this guy and make it look like the rectangle. Right. So the basic pipeline here looks something like this. So at the end of the day, if I want to render the bunny, what I'm going to do is every triangle in this bunny is going to have two sets of coordinates. Okay, there's going to be the coordinates of the points on the 3D shape. Right. This is telling me the actual geometry sitting in 3D. And now I'm going to have a new set of coordinates, which is a triangle inside of the image plane. And I'm going to kind of think of these two guys as being mapped to one another. Does that make sense? So what is my ray tracing pipeline going to look like? I'm going to take a ray out of my eye, I'm going to point at the bunny, and it's going to run into this green point here. Right? And what information do I get when I figure out that my ray hit a triangle? Remember back 3 lectures ago? What do I compute? Set of numbers, they sum to 1, they're between 0 and 1. Don't all speak at once? Yes, louder. Barycentric coordinates, exactly. Right? So that's the coordinates inside of the triangle of this green guy. So now I'm going to do something sneaky, which is I have another triangle over here. Yeah? And I'm going to compute a point whose barycentric coordinates are the same in the interior of this 2D triangle. Right? And now this is some new point in the image plane. And that's the color that I'm going to read off for the pixel over here. Does that make sense? So that's our basic algorithm. It's pretty straightforward. Right. And what that allows us to do, obviously, is we change our camera angle. Essentially, what we're doing is shifting around our coordinates in the plane. And already you can see some challenges here. What do you notice? Does this, if I showed you this in a vacuum, like, could you guess it was a bunny? Maybe. It has very seductive eyes. But no, I think like the reality is this is like a kind of a disembodied shape over here. And a lot of the big challenges in texture mapping come, for example, from the fact that I could move a small distance along the surface and hop into one of these other patches down here. And that's kind of necessary, right? Because topologically, the bunny is a sphere, right? Like in other words, it's just a big ball, but this is a patch on the plane, and those are two different objects. So in other words, I gotta tear them apart somewhere. Right? And this is where the UV mapping artists really come into play, because they carefully place these seams in places where they think you're not going to see them, like behind the ears and so on. Yeah? I think there's a lot of characters in Toy Story or whatever where if you rendered them from the right angle, you could see some pretty bad discontinuity. And so there's a little bit of like the drama in your scene is guided in such a way that you don't see a bad texture. It's like kind of sneaky. Okay. Right. So again, here's this algorithm I described for you guys in words, right? So here's my 3D triangle, which are all these nice colors here, and I compute the alpha, beta, gamma, which are the barycentric coordinates in 3D, and then I just use those barycentric coordinates to find a point in 2D. Right? So notice I did an inverse problem here and a forward problem there. Does that make sense? I went from 3D to barycenter here, and then from barycenter to 2D here. And now reading off a color on an image is an easy thing to do. Yeah, and that's how I do my rendering. Everybody with me so far? It's going to be real boring if you're lost now. Cool. Okay. So this procedure is called a texture lookup, for obvious reasons. Yeah. And essentially the idea is that actually, oftentimes on your graphics card, you'll have a dedicated piece of memory whose job in life is to hold two-dimensional arrays. And those two-dimensional arrays are images that are intended as textures. And so actually a large part of the hardware in your graphics card and your computer is intended to make random access into a 2D grid as fast as possible, because this is the thing that has to happen for a pixel. Right? And so this is accelerated a ton. Okay, so now that we've written down this pipeline here, what goes wrong? Why could texture mapping be problematic? When could I get an ugly image by doing this? Actually, this image is a good example. Like, you know, in principle, I'd like to have something that looks like a hand with wrinkly skin. Yeah.
I don't know if this is the problem. But I feel like if you view the triangle at a weird angle, then it will not map well.
Yeah, that's exactly what I was thinking about. Or an even better one is, let's say that my image plane is somewhere over here, and I'm rendering a tiny little hand. You know, it's a presidential hand, it's far, far away. There it is. Yeah, and roughly, you know, I draw my rays, and my pixel is like that. Okay, so the entire tiny hand is caught inside of one pixel of my image. Okay, so how many pixels does that one pixel correspond to in texture memory here? It's like some big triangle on the right hand side. So when I ask you what color I should shade, what color should that be? Well, should it be just that one point at that barycentric coordinate? Well, think what would happen then, right? So now I take, maybe the hand stretches across 2 pixels, a little bigger, yeah? And I choose, here's one pixel center, and here's another one. Where are these going to show up in texture memory? Like in totally far away locations. Do you see that? So if I have this extremely high frequency texture, and I just sample one point, and then I choose some other point all the way over here, what do you think the image is going to look like when I render? Noise, right? Because take a look, just in some tiny little neighborhood in this image of somebody's hand here, it's like kind of grossing me out because I'm like a little too close to it. There's like kind of orange color, there's white, there's black, right? And if there's like some tiny amount of error that corresponds to basically all within 1 pixel, but of course there's a big change in color, then if my pixels are sampled like far, far apart in texture space, it's just going to look like aliasing, right? It's just going to look like big high frequency noise. Yeah? And so that's one big issue here. The other big issue, which is actually slightly easier to cope with, is what if I get all up in its business, and now I have a bunch of pixels, you know, I have a bunch of points on my triangle that are all inside of the same pixel here. Then I'm kind of back at my old scenario, right? I'm going to start to see discontinuities. Yeah, and these are the kinds of things that we worry about in the texture mapping world. That like we're not just looking at this as a photograph anymore. We're kind of taking this photograph and warping it onto a triangle and then rendering that. And that process of warping onto a triangle could squeeze lots of information into 1 pixel, or it could stretch it out over a big piece of the screen. And both of those are quite problematic. Yeah? So that's the thing to keep in mind as we talk about this stuff. Any ideas how to fix the tiny hand problem? What's the solution to all ray tracing problems?
More rays.
More rays. Thank you. You should all wake up in the morning and say that 3 times. Right? This is biggie smalls, biggie smalls, biggie smalls, more rays, more rays, more rays. And indeed, if I took a bunch of rays to this pixel and kind of average, maybe I could account for that noise a little bit. Any idea what that procedure is called? I'll give you a hint. I called it aliasing a second ago. Anti-aliasing. Excellent. See, you guys don't need me. Okay. Right. So anyway, these are issues I wanted to kind of suggest a little bit, and for you guys to cook over while we talk about the basic algorithms, and then you're going to tell me how to solve them when we get to that point. Okay. So right. So remember, our ray casting algorithm is pretty simple. I think at this point I've repeated myself 10 times. Right. So the basic procedure, whether you're rasterizing or ray tracing, is the same. Right. Now you just have kind of a bunch of different coordinate systems you have to juggle all at the same time. Right. There's the 2D image and the 3D shape, and these things are mapped to one another. Yeah. Sorry. I was going to say something a bit. Okay, so let's say that we're dealing with the case where the hand is like right up in my face, and now I have, you know, a giant pixel which is bigger than the shape of my triangle. And what do I want to do? Well, I don't really want to see a pixel grid in my rendered shape. That wouldn't look too nice, right? So typically what we do is we think our image, our texture image, as being sampled at kind of discrete points, right? These feel like the centers of the pixels, maybe. And then in between, we might interpolate, yeah? And there are many different ways to interpolate. What is this going to start to sound like? It's from like weeks 1 and 2. You got to start getting ready for your midterm. Splines, right? So we're going to talk about a really simple technique now, which is just basically linear. But it is true that the higher order splines are exactly what people use to do interpolation in texture space. Sorry guys, it's inescapable in this class. Okay. So let's say that I'm rendering a triangle. My pixel locations are at the corners here. I do my ray intersection. I end up at this point. What is a man to do? How do I choose a color for this pixel? Well, the simplest thing to do might be to round. You know, just find the closest by thing. But of course, the rendered image, then you're going to see this unnatural boundary between pixels, which is probably not so great. So instead, the kind of typical thing to do is known as bilinear interpolation. It's exactly what it sounds like. Yeah? And it looks like this. So let's say I had that. Remember, our pixel position was somewhere over here. I'm sorry, I removed it. So one thing I could do is interpolate first just in Y. Right? We know how to do that linearly. That's something we've already talked about. Or interpolate in X. So say interpolate it in X. So now I get kind of a greenish color and a bluish color. Right? So if this is like t equals 0, this is t equals 1, then we get some linear combination of those two colors. And now I could just do the same thing vertically. Right? Connect those two with the line, and out comes my color. It's a pretty simple calculation. I think you guys could all derive the formula by hand. Lemma that you should prove, if you want to call it that, is notice we made kind of a funny decision, which is I said interpolate this way and then that way. You might ask the question of like, what if I interpolate the linear linear that way and then this way? Does it change? The answer is no. But that's the thing you should check, right? That's not obvious the way I've defined it. But in any event, this is called bilinear interpolation, and it's good enough so that if I'm in this case where I'm right on top of the surface, at least I won't see a sharp edge that should be there. Does that make sense? Okay, so later on, when I have budgeted one lecture to teach you all Fourier analysis, which will be an interesting exercise. We'll talk about some better techniques for interpolation that are more representative of sampling and reconstruction. But for now, this will at least get us something smooth, and it's kind of a reasonable thing to do. Yeah? Okay. However, I think the larger issue is not when there's a big image and a small texture map, but the other way around. Which I think is actually subtle in a sense, right? Because in some sense, if I asked you how to make your texture better, you'd say get a bigger texture. But that's actually not true, right? Because here, if I have two close-by pixels on this image of a small hand, they become far apart in this texture, and just depending on small perturbation, it might be like white, it might be orange, and so on, right? So adjacent pixels could just be totally wildly different colors. So in reality, I think the way that we kind of reason about this, and again, we're going to suggest some ideas now, and then we're going to explore them over the next few lectures, is that really a pixel over here, in this case, kind of corresponds to a region over here. And that's because our pixels are kind of a finite distance apart from one another. Yeah? And so in a sense, what we'd really like to do is to capture the integral of this function over this entire thing, like to kind of average the color in some neighborhood of the purple point. Does that make sense? Could we do that in principle? Absolutely, right? I mean, we could kind of compute the boundaries of this square, like just compute the 4 corners of the pixel and just take a big average on the image. What's going to be the problem with that? Slow, right? Because like now for every pixel, I'm not just looking up once in the texture map. I'm having to like do a computation over here. And that's a pricey thing. You know? And so there's a really sneaky thing that we do in ray tracing and in rasterization. This is called MIP mapping. Has any of you guys ever played with the MIP map before? I just like saying, yeah? So the idea of a MIP map, it actually stands for a Latin phrase, it's multum in parvo, which I guess means much in little, is that before we begin the rendering process, we're going to compute not just one version of our texture, but a bunch. We're going to take like a big texture, one that's half as big as that, smaller, 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 smaller. Cool? And why do we do that? Well, one pixel, and notice that like having the size of an image is pretty easy to do, right? Like every pixel here is the average of 4 pixel colors there. So now when I'm rasterizing this triangle, if it's far, far away, I choose the texture map so that roughly the spacing between pixels here is the same as the spacing between pixels in my image. And that way I don't run into that aliasing problem. That's sneaky, huh? As an additional sneaky trick, here's a good question for you. How much memory does a mip-map take? Yeah?
Like half or 1.5.
1.5 times the amount. That's absolutely right. Do you guys know why? This is a sneaky, sneaky trick on the part of the mip-mapping people. Actually, this image kind of suggests what's going on. So first of all, let's say that my original texture image has n pixels, right? How many pixels are in the next image down?
N over 4.
N over 4, right? Because it halves both in x and in y. It's a plus. Okay, so how many images are in the next guy, next level now? Well, it's half of the number of this guy. It's n over 4 squared. Right? Yeah, and if you do that, so of course in reality it's finite, like you hit 1 pixel and you're done, but maybe we'll be generous and allow ourselves to just keep adding stuff. Right, so in other words, this is and the sum of 1 over 4 to the k. I'm not good at geometric series, but eyeballing for this thing, it looks like it's about 1 3/4. Anybody know geometric series formula? I always forget. 1 plus 1/4 plus 1/16 plus 1
1 minus r.
1 over 1 minus r? Oh, yeah. Oh, so I got it right by which indeed, so that's 3/4. So this is equal to 4 n over 3. I'm going to put a question mark here because I don't remember the formula. I'm trusting this gentleman here, which I'm sure he's probably right, but whatever. But the point here is it's finite, right? And so I can store a bunch of rescalings of my image, and this doesn't take a whole lot of extra memory, right? And what I gain is that rather than having to average over big regions in my original texture, I've kind of done that ahead of time by shrinking my image to different scales. See, this is called MIP mapping. Now, what's the problem with MIP mapping? I told you it gets rid of this like kind of discontinuity between pixels. Yeah? But instead, it adds a new discontinuity, which is between 2 adjacent pixels. At some point, you might decide I need, like think about, I'm trying to think, using our hand texture analogy thing. If I'm rendering my arm like that, yeah, and I'm really close to my eye, I'm going to need like this piece of the mip map, and then far away, I'm going to need like over here somewhere. So somewhere in the middle of my arm, I'm going to see a cut where I transition from one mip map to another. So a pretty standard thing to do is actually to use 2 mip-map levels and then kind of average them together so that like you smoothly transition from one to the next. Right? Just using that bilinear interpolation trick one more time. Okay, so we'll discuss this a little more when we talk about sampling and talk about why this is justified and the best way to actually compute the mip-map. This turns out to actually be kind of simple. So the example I want you guys to all think about when you go home, if you haven't figured it out, I know this is a topic I really like, so I'm having fun with it. Let's say that I have a checkerboard, like that. Whatever. And the width of every checker is, say, 4 pixels. what happens if I make my mid-map and I just take every pixel in my half size to be the average of 4 pixels here? It just looks like a checkerboard again, right? It doesn't actually look any blurry. And that's possibly fishy, right? Somehow I didn't actually get as smooth transitions as I shrunk this thing. And that's because the reality is if you want to summarize the neighborhood around a pixel, you need kind of a Gaussian decay that goes around it. And working out precisely the right convolution filter is something we'll do in a few lectures. Just so you think about it. Anybody happen to know what that filter should be? If you've taken electrical engineering, you've probably seen it. It's also the logo of a lot of EE companies. It looks like, it's actually not a Gaussian. Where that should go. It's called sync. Anyway, we'll come back to that. Okay, right. So a good vocabulary word to remember is UV coordinates. And this is the idea that every triangle now has 2 sets of coordinates, right? The position in 3D and the position in UV, which is texture space, right? Because typically the letters X, Y, and Z are already taken up for the 3D stuff. Okay? And a key question to ask is like, okay, but who made those UV coordinates? Like, this is itself kind of a hard problem. And this is actually a thing that people spend quite a lot of time thinking about. So often there's a lot of different software products out there. They typically look something like the screenshot I've shown you here for flattening an object into 2D, right? Because this is what you need to have texture coordinates. And so what they'll do is they'll effectively ask the artist to take a pair of scissors to this guy's head here and kind of cut him up in just the right way, and then place all the vertices in the interior. Right, so a very typical visualization of this is to put a checkerboard texture down here and then show what it looks like in 3D. Do you guys know why? Why would that be useful? Like, what's a good property of a texture map? Be one probably where all of these little squares are approximately the same size. Right? Because what that means is that it's not like 90% of my face is all of this tiny little bit of the texture and the rest of it is spread out. Right? Because you kind of want an even spread of resolution across the 3D mesh surface. Does that make sense? Cool. There's all kinds of software tools for this. So here's in 3D Studio Max, here's a kind of production pipeline what this looks like. By the way, it also is true for quads, not just for triangles. And there's actually, if you flip through digital art textbooks, you'll see that there's a lot of rules of thumb of where artists tend to place these scenes, right? So I think the typical thing to do is to kind of place them right underneath the arm so that you just don't notice, or behind the ears, because those are the kinds of places where you're just unlikely to see them in rendering, because it could cause a tiny bit of artifact. Yeah? Is this science? No, this is just some rules of thumb that artists use for placing this thing. But if you guys are math students, and I know some of you are, this is kind of an interesting point where you should notice that essentially what's going on is we're coping with a topological problem here, right? Like this guy is a 3D shape, he's a surface, he has some number of holes. The plane is the plane. You're trying to smash one into the other, and in order to do that, mathematically you have to cut it somewhere. And so coming up with algorithms that do this automatically is quite challenging. The reason I'm so excited is because this happens to be the topic my research group studies. And so, in fact, even just last year, there are all kinds of interesting research problems that we continue to study in this area. So one of them is actually, even after you decide where to cut your 3D surface, like a cow here, you could ask for how do you map this thing into the plane? Right? And there are all kinds of different criteria to consider here. Right? One of them is, you want the edge lengths of the triangles downstairs to approximately resemble the edge lengths of the triangles upstairs. You'd like the length of your cut not to be too big. And perhaps the most difficult constraint here, which is a little bit subtle, is if any two triangles overlap in the plane, the entire parameterization is useless. Do you see that? Because if I put a texture down here, I put my spots on my cow, and two triangles overlap, that means they have to have the same spot, which is not so good. Yeah? And so if you think about it, how many of you guys have taken any class where you're minimizing some function f of x, subject to g of x equals 0? Think about that g of x for a second. But there's actually a quadratic number of terms that appear in this problem for every pair of triangles, saying that they can't occupy the same piece of the plane. Yeah? So it's a number crunching problem. It's really tricky. And this is after somebody tells you where to cut, right? The other question you might ask is actually where to cut the surface. And this is what we call coming up with a texture atlas. This is a term that comes from differential geometry. You have a surface and you cover up little patches. That's called an atlas. And actually, coming up with texture atlases automatically is an open problem. This is a thing people study. Right? So typically, what these UV mapping tools do in software is they ask the artist to kind of draw these curves, which are where the surface is going to be cut. And then the software will automatically map every patch using one of these numerical tools. Just recently, actually, coming in just a few months, there's some automatic tools for doing this. And they're really fun to watch. I thought I'd share. So this is, and then I'll show up and show you the basic contents of the class. So the tools for these kinds of problems kind of look like what I'm showing you here. They come up with some terrible initial guess for the parameterization. And then what they're kind of doing is taking scissors and cutting along the surface to reduce the distortion. And then when the distortion is close and like two pieces are kind of nearby each other, maybe it tries to glue them together and sees if that makes things bad or not. And you can see that slowly over time it converges to a nice mapping of your match. Let's see, maybe we'll zoom to a more interesting example. Yeah, so here, oh no, I gave it away. Right, so here's the initial parameterization as a single triangle. And eventually, as you reduce the distortion, you can see on the right-hand side, it's tracing out where the cuts are happening, are these orange curves, and trying to reduce the distortion at the same time. The kind of amazing thing that you guys should get from this is until like the last year or two, there are a couple of people, not just our research group, that study this problem. Until about a year or two ago, this was a problem that we asked artists to do by hand. And so you can imagine that this is actually a really expensive piece of the graphics pipeline. It's coming up with good texture maps that have low distortion, cuts that are hidden away from view, and so on. It's a great application of both math and computing and art all in one shot. Yeah. These are really fun to watch. Okay. Anyway. Oops. Right, so anyway, at the end of the day, hopefully what I want to convince you is that texture mapping is hard, but there do exist some tools out there for solving it, whether it's yeah.
Oh, just out of curiosity, what exactly like triggered like the rip from like, so before with the octopus,
Yeah?
there was this moment where everything was kind of one unit,
Mm-hmm.
then after further like steps of optimization, they just decided to rip.
Yeah, so in this particular tool, what's going on, so the easiest way to parameterize a surface is to unglue every single triangle and parameterize every single one into the plane individually. And if you think about it, you can do that with zero distortion, but that's not so good because the cuts are everywhere, so you tend to see a lot of seams in your texture. And so the way that this particular tool is designed, which is pretty typical, is that there's a trade-off between the length of the cut and the distortion. Right? And so what this is doing is iteratively trying to reduce that. And so for a while, like when I've mapped this entire object to like one triangle, the distortion is so large that the best way to reduce the total cost is just to move around the triangles. And then at some point, if you think about it kind of like a rubber sheet, so initially I push the sheet in and all the points kind of squash out. And then at some point it begins to tear. And that's what you're seeing there, is that there's sort of some stress that's pulling it apart. In fact, a lot of the algorithms in this space have a lot to do with fracture mechanics. So people that study, like, I take kind of a gooey object and I throw it against the wall and it splats and tears apart. And that's roughly what these algorithms are doing. They're just like taking the shape and then like taking a hammer and smashing it into the plane until it's flat. Yeah. But doing that algorithmically is pretty challenging. Let me see, I think the next example here is kind of a lot. I forget what Min Chen put in this video. Oh, no, it's okay. Thanks. Okay. Right. Yeah. So at the end of the day, here's the thing about that procedure is it happens offline, right? This is something that happens to analyze a 3D surface before you begin rendering, so you can afford some of these kind of expensive number crunching routines, because then you're going to use that texture map over many, many frames when you're rendering. Yeah? So of course the next thing we should do is render. Before we do that, I thought I'd mention briefly that there are some tricks for easier texture mapping than these wild and crazy algorithms. Some of the simpler ones include, for one, you could just have a really simple algorithm that, for example, in image-based rendering, this is pretty common. If you have a 3D model, like the Starbucks cup, maybe I just take a photograph of it from like a few different sides, and then my texture map is just kind of like the silhouette of this object projected into the plane. Right? That would be kind of a reasonable thing to do. You get into trouble there, like for this coffee cup, it will work pretty well. if you like had a donut with a bunch of holes in it and like things where you need a bunch of crazy camera angles to capture all the pixels, you'd be in a lot of trouble, right? But in any event, you know, if you're rendering soup cans, or even this bunny is like kind of planar in a funny way, like if you slice it this way, you can see most of the surface. Then maybe that's a reasonable thing to do. And so a pretty common thing to do is for like kind of canonical shapes, like spheres and soup cans and so on. Like if I asked you guys to come up with a function of f of gamma and phi into the sphere, you probably could, right? Spherical coordinates, you probably remember from calculus class, I hope. Right, then that gives you a reasonable texture map, at least for these special shapes. Another thing people do, this is a little outdated I think, but it used to be that you didn't want to store texture coordinates because that was 2 extra numbers per vertex on your triangle mesh that you have to store, and that meant, you know, multiplies your memory capacity by 2/5 or something like that. I guess that's totally wrong. Whatever. It makes the amount of space you need bigger. Yeah. And so people came up with kind of closed form formulas for texture maps that you could evaluate on the fly. Another one would be to take the 3D model and kind of reverse the rendering process in a sense, like store an image and a camera pose, right? And say that the texture at some triangle, now I'm going to do ray tracing the other way through back to the camera and intersect with the image plane, and that's the texture coordinate. That's an okay thing to do, but of course it only works as long as you don't look at the other side of this kettle here. But it is something that you can just compute, and it gets used sometimes in image-based rendering. So in the cases where you like actually take a video of an object and then you just want to render it from another camera angle, then it makes a lot of sense, right? Because you kind of pick a point on that 3D object, you pick a frame in your video sequence that can see that point, and then you just read off the coordinates in that image. And so like there's a famous old video here, which hopefully we'll play. It's from this terrible school in the North Bay. And it's also very 80s, which uses exactly this technique, right? So they did image-based rendering where they captured the campanile, which is the bell tower at Berkeley. Boo, terrible football team. And what comes out here, as we'll see, in T minus something. This is great acting by my colleague here. That they're able to composite the image together, right? And so there's one texture map going on behind the scenes, which is just the environment around the campanile, and then this is just this kind of simple projective texturing, right? So what's going on here is as they have some simple geometry for the campanile, they're lucky because it's essentially a rectangle glued together with a pyramid, and so you choose a point on here, and then you choose a point in their video sequence that can see that point on the campanile. That's how they choose the color. Yeah? And this allows you to do all kinds of psychedelic flight losing. Right, a more kind of modern pipeline, which is still pretty easy for texture coordinates, is to use barycentric parameterization. This is an algorithm we'll cover in detail in my course in the spring, but roughly, once you have the boundary of a UV map, one reasonable thing to ask might be that every internal vertex is the average of his neighboring vertices. Do you guys get the philosophy here? So my goal here is I have a triangle mesh which happens to have topology with disks, so like a circle. And now somebody glues the boundary of the disk onto the plane and I'm trying to place all the remaining vertices. Yeah? And so one thing you could do, as sort of an ansatz for good parameterization, is say, I have a vertex, and I don't know his position, but I do know maybe the neighboring vertex positions. So what would be like the kind of a reasonable way to place this guy is just as an average of his neighbors. Yeah? Because kind of for lack of a better thing to do. So one thing you could do is actually solve a linear system, which says for every unknown vertex, it should be the average of his neighbors, which are also unknown. Yeah? If you think about it, that's a linear condition. And so what you end up with is a giant matrix to invert, and that gives you the positions of all the internal vertices as a function of just the stuff on the boundary. This is called harmonic parameterization, and if you've taken a PDE class in the maths department, you'll know why. Otherwise, it doesn't matter. It's still kind of a reasonable thing to do, right? You're just placing things at the average level. Okay. Some additional tricks that you guys should know about in the texture coordinate world. One of them is tiling. So if I want to render a brick building, it's probably overkill to like store a giant brick texture. Right? So instead what I might do is sneakily design a texture with periodic boundary condition, meaning that sort of the pixels on the top of my texture, the pixels on the boundary on the bottom of my texture are the same color. Right? So that way if I keep wrapping up this way, I'll just get more and more bricks. This person has actually done a very poor job of that. You can see the line. But this is a very common thing to do, especially in video games where you have like big buildings that are brick or stone or whatever. They maybe will store kind of a tiny swatch of stones, but they'll ask the artist to design it in such a way that the boundaries meet up. That seems like a difficult thing to do, but in reality it's actually not that hard. The trick is actually to change the user interface that the artist sees. So what you'll do is you'll say, okay, your job is to paint a brick inside of this square, but as you do that, I'm going to render for you, like if I draw a pixel here, it's actually going to draw a pixel repeated a bunch of times. And so that way, if the artist draws a stroke like this, right, then as they go across this line, right, they'll see it on both sides. And so this is a kind of a tricky user interface to force somebody to think about the right boundary conditions as they draw the texture. You guys see that? It's kind of sneaky. So it's actually not that hard. I mean, initially, I think when you look at a texture, it's like something you might think is like kind of tricky. How do I make bricks and guarantee the sides meet up? But in reality, it's not too bad. A different question in image processing, which is challenging, is if I take a photo, for example, of your chair here, and I say, okay, I would like a texture with periodic boundary conditions that looks something like the back of the chair. That's a tricky computer vision problem that we'll save for another day. And that day will not be over this semester. Okay. Right. So at the end of the day, what did we notice? We noticed that effectively what I've given you is a piece of machinery that can read off detailed information per point on a surface at a sub-triangle resolution. Hopefully that sentence parses for you guys. And what it's saying is that inside of the triangle, the texture can vary, and that's an okay thing to do. Yeah? And the obvious thing to do would be to store color, but if you remember our Phong model, notice it contains 3 terms, right? Ambient, diffuse, and specular. It doesn't have retro, whatever, on our nano quiz. What is retro reflection? That's the one where the reflected ray comes back in the same direction that it came in. I forget what kind of surface has that. Anyway. So you notice there's a ton of parameters in Phong shading, right? I mean, there's Q, there's the different light colors and so on. And you can store all of these in different texture maps and vary them along the surface. And that's perfectly fine, right? Because remember, our shading algorithm is kind of independent per pixel, right? So essentially all you do is read off that information and then evaluate the PRDF. And indeed, that can make some really impressive effects. I forget if this is a video clip. No, it's not. So here is a rusty piece of metal, yeah? And so what have they done? Well, the rusty part of the metal has a BRDF with a very low specular coefficient. I sound very scientific when I say that. But what it means is it's not shiny, yeah? And here, the shiny part of the metal has very high specular coefficient because it is shiny, right? So if this thing is modeled using like 2 giant triangles, right, then the best you could do with the previous lecture is just 1 giant shiny object. But here, by mapping it into a texture, the texture map here is determining the BRDF in a local fashion, really without any additional computation, right? So it's not like this somehow makes your code much slower, unlike all these ray tracing effects where you need lots more rays. Does that make sense to all you guys? And in fact, there's all kinds of cool stuff that we can store locally. It's not just BRDF parameters. One really sneaky one that I think we mentioned a few lectures ago is you can actually store the normal vector to your surface in a texture map. This sounds kind of crazy, but if you think about it, it aligns well with, remember we talked at the end of the lecture about microfacets for rendering? The idea that when you see a rough texture, really what's going on, or like when you see certain materials, what's going on is if you took a microscope to them, it would be some rough texture. So one thing you could do would be to say, yeah, my triangle is flat, but that's not really the normal I should use for rendering. The normal I should use is like some function along the surface. And this can create some really convincing effects. And this is actually one of the primary things people do in graphics world. It's called normal mapping, or sometimes bump mapping. Although bump mapping is overloaded with a few techniques that are all kind of similar. And the basic idea here is if you look back to our Fong model, remember we had this n.l term, but there, God didn't say the n had to come from the triangle. It could come from anywhere, right? And indeed, what you can do is along the triangle, like slightly perturb the normal in different ways to create interesting effects. There are a lot of reasons to do that. One of them is because it's cool, but probably a more interesting one is actually for compression. Yeah. So here's an example. So here, this is, I believe, a 3D scan of some clay object or another. My buddy Paulo has scanned, and there's 4 million triangles. This is a pretty typical output of a structured light scanner, I think. Yeah, and this is an extremely detailed mesh. But if you kind of step back, yeah, there's like local variations in the normal. But really, it could be approximated pretty well with a smooth surface. Do you see that? But if I did that, it would render poorly, right? It would look like a smooth object. This sounds kind of weird. So the question is, well, why do I say that it can be approximated with something smooth, even though I want all this crazy texture here, right? And the reason is that there's sort of two roles that crazy texture serves, right? One of them is just to see this interesting stuff. The other is occlusion, right? That like if I have a surface that varies wildly up and down, then different parts of the surface occlude each other. And I would argue that occlusion is not terribly significant at the coarse scale, at the fine scale. You see, that really the main occlusion is like his beard and his schnoz. It's not like imperfections in the material. Yeah. So what Paulo does, which is sneaky, is says, okay, I'm going to simplify this mesh a bunch, like really aggressively to get that guy on the left-hand side. But I'm going to remember, I'm going to at the same time, I'm going to generate a texture map underneath every triangle, which just reads off the normals from the original model. You can do this pretty simply, like at every point here, kind of choose the closest point on the old mesh and read off as normal. And when you render it with normal mapping, what do you see? It looks almost exactly the same. I say almost. You can, if you spot, there are a few differences. Let me see if I can find one. Yeah, so one of them is right here on his beard. You see this little singular point? This is because the mesh simplification algorithm is not so good there, right? And so here is an example where the occlusion actually mattered, and it got a little messed up in simplifying. But for the most part, it's actually a really positive result. And the kind of cool thing is, like, if I'm doing specular highlights and all these things that depend on normals, as I rotate this surface, I'll still see fine scale effects. It's not like it's just some coarse, some texture that's painted on there, because I'm still doing the BRDF computation per pixel. Do you guys see that? So that's the really sneaky trick here. And this is a really classic effect, and one that people have done in graphics forever. So for instance, here's a production model of some robot arm or something, and you can see, for one, the texture map here is quite complicated. This person has worked very hard to solve yet another problem, which is, after I take this surface, cut it up, and take every piece and parameterize it, the next thing I want to do is lay them out on the image plane to take as little space as possible. That is itself a challenging geometry problem. If you like that kind of stuff, I encourage you to take Kyoto's geometry class. But along with just storing the diffuse texture, they also store a normal map, which is creating some of these cool metallic effects and boundaries of shapes and so on. Cool. So as one algorithm for generating normal maps, which we already kind of suggested a little bit, maybe you have this detailed mesh like the guy with the beard, and now you UV parameterize that detailed mesh. Okay. So you saw one of the problems we had before, then you simplify it. Essentially what you're going to do is overlay those two guys on top of each other, and for every pixel in your texture map, you're going to read off the normal from the original parameterization. That makes sense? Cool. All right, so yeah, this is a sneaky trick in rendering, and one of the common tricks of the trade that you guys should know. Because the complexity of reading a number off of a texture map is very low, right? So in terms of efficiency, this is much, much better than like adding a million triangles to your scene that you have to intersect your brain with. Yeah? Okay. There are a few details that are worth thinking about a little bit. One is, what would be kind of annoying is if your normal map just stored a normal as an XYZ coordinate. You see that? Because like, typically we have surfaces that bend and deform and rotate, right? And if my normal is XYZ, then like I have to stay in this one pose forever. Because if I move my arm, my normal would still point with the original guy. Right? And so typically what you do is you store it relative to the coordinate system of the triangle, which is a pretty reasonable thing to do. And if you want a really, really big headache to think about, one is things like tiling when you're on a curved surface is really tricky. This is there's a vocabulary word here called holonomy. The basic idea is if I take a texture patch, I drag it around a surface in a loop, and I bring it back to where it started, oftentimes it'll rotate in that process. And that can itself create seams and distortion, and people worry a lot about that. It's like one of these fundamental math problems that just comes hiding in an application. So for many years, engineers thought about it, and then finally we kind of realized, like, no, this is a math problem. But anyway, that detail aside, any questions about our story so far? I think this is really cool stuff. Like these are neat tricks that people have thought about carefully. Okay, so very briefly for our last 20 or so minutes here, we're going to talk about a very different type of shading called procedural shading. And this is sort of the beginning of our discussion of procedural rendering, right? So the idea is that texture mapping isn't that interesting from like a programming perspective, right? You're just kind of reading off numbers from a grid and using them for rendering. But you can also think about writing code that generates a texture on the fly. Right? And this is a big tip of an iceberg and leads to all kinds of interesting ideas, right? So for instance, one thing that people look a lot at is if I have a big data set where I know roughly where buildings are in a city, can I generate a new city procedurally so that if I have some like video game where I'm driving cars, I can just keep driving forever and stay on something that looks like a city block. But for today, we're gonna look at a more local thing, which is just generating materials that have some kind of macro scale property, but still some randomness hiding in there too. And so this is kind of like the material class in your ray tracing homework, which I'm sure you have all started by now. So the idea is that, remember in our ray tracer, there's sort of two steps, right? The first is we intersect a ray with the scene, and then we do this calculation, which is what color should that object be? Yeah? And a shader is that second half. It's a little function which says, given information about where I am on the surface, and the texture on the surface, and the normal, and the position of the light, all that kind of stuff. You know, the input or radiance, whatever, maybe some additional stuff. Output, just the reflected color. Yeah. That reflected color, sometimes called a fragment, although that's more OpenGL speak. We'll come back to that later. And these are used both in production rendering and in real time. So for now, we'll think about it in terms of kind of slow rendering, like what's in your ray tracer. Like that material class that you wrote is arguably a shader, although it's in C++, it's not in its own shading language. But nowadays, it's really popular in real time programming. It actually was also the beginning of some of the computer vision revolution that we had. Because the basic idea of a shader is that it's a programmable unit inside of your graphics card. And then people started to hack them to do stuff other than rendering. And that was the beginning of people realizing, like, oh my god, my graphics card is this really powerful tool for like statistics, right? Where I was writing shaders that weren't like shading colors, but like shading data points, which was really clever. Okay, right. So the basic idea here is to talk about procedural texturing. And this is an alternative to texture mapping. And a great example is shown here. So here, we have this big, giant, infinite red and yellow checkerboard here. And it would be kind of overkill to store this texture as a photograph. It'd be a really boring photograph, right? So instead, what could I do? I could like compute the x and y coordinate in the plane and say, well, if my x coordinate is even and my y coordinate is even, make it red. If they're both odd, make it also red. If one of them's odd and one of them's even, make it yellow. Almost fell for that. And that would make a coordinate, a color, just as a function of position. You see that? This is a very simple example of a procedural texture, right? I wrote a piece of code that, given information about my scene, generated a color, right? It didn't like look it up in the language. Yeah, and of course this is a very simple example, but there are many. And really the advantage here is that they tend to be easy to implement and relatively efficient. And you can do all kinds of crazy things like have solid textures. So maybe I'm texturing a tree trunk. It would be kind of expensive to store a whole volume worth of colors. So maybe I come up with some procedure for just generating them on the fly. But on the other hand, I'm asking you to write code, right? So if you're an artist, it might be easier to paint a texture than it is to write a little piece of code to generate it. So the reality is the graphics pipeline typically includes both, and depending on the object you're modeling, one or the other might be useful. Does basic vocabulary make sense here? Right, so the two extremes are texture mapping and procedural texturing. Okay, so we're going to talk really quickly about one very popular model for building up procedural textures. This is called Perlin noise. I've included a billion different links to go, you guys go play with Perlin noise at home. And this is something called a pseudo-random function. And if you look really closely at a lot of, I'd say, kind of amateurish rendered scenes, you can often spot Perlin noise pretty easily. Because Perlin noise tends to make texture that kind of looks like this thing. So it's like kind of random, but low frequency. Right? Like clearly here, I didn't just choose a random color per pixel, right? Because that would look like TV noise. Does TV noise make sense to you guys? All these millennial kids here, you remember old TVs with the you know, black and white stuff? Yeah, like clearly that's not the case here, right? Nearby pixels are correlated with one another, but it's still changing along the image plane. Yep. And so the basic trick in Perlin noise is to generate a bunch of these things at different scales and then to composite to them together in clever ways. Yep. And this sounds goofy, but it's actually quite powerful. Let's see some examples in a second. And so the basic tricks are that it's going to be something called pseudo-random. The reason it's pseudo-random is because we're going to decide on a list of random numbers to start, and then we're going to use them for rendering for efficiency purposes. And it's sort of smooth, or at least bandpass, meaning that I'm going to give you some scale at which it's random and some scale at which it's not. Right? Like so, for instance, in this image, it's random at about this scale. Do you see that? This is obviously a very heuristic language I'm using. Exactly. Okay. So how would you guys do this actually? How would you go about making pseudo-random noise? Like if I said, about every 10 pixels, I'd like my image to look random, but between them I'd like it to look kind of smooth. What do I do to make things look smooth? Yeah.
Interpolate.
What's that?
Interpolate.
Interpolate! And how do we interpolate?
Splines.
Splines! Exactly. So this is yet another example where splines appear in the graphics pipeline. And in this case, are really in an elegant fashion. Right? So for instance, let's say that I have Perlin noise, and I'd like that my randomness happens at about the integer grid location. So between every integer, it's kind of smoothish. And that I'd like my noise to be zero mean, meaning it kind of averages to zero. Then a reasonable way to generate noise, and this is exactly what Perlin proposed, is at every integer point here, I'm not going to generate a random value for my function, because I want it to average out to zero anyway. But instead, I'm going to generate a random slope. Yeah? And remember, if I have 2 points and 2 slopes, right, see? And I want the value of my curve in between, what is that called? Anybody remember? That's a good review. What kind of spline is that? Starts with an H, ends with Hermite. Yeah, this is an Hermite spline. Yeah. So essentially, Perlin noise at a single octave or a single spacing here. It's just I randomly generate a list of slopes, and then in between every point, I use an Hermite spline to interpolate. So this is a pretty reasonable thing to do. In the slides, we go through the math. But here's the thing about this math. It's exactly the same as what we did for Hermite splines, so we're going to skip it. In reality, of course, we want 3D noise. So we're going to kind of combine that Hermite spline idea with the bilinear interpolation that we talked about earlier in today's lecture, right? Because remember the bilinear interpolation algorithm? We kind of interpolated in X and then in Y, right? So we only ever needed a one-dimensional spline to solve that problem. So we can do exactly the same thing for Perlin noise, right? If I want the value inside of this cubic lattice somewhere, I interpolate all of my slopes to in every dimension one at a time to get the value that I want. Does that make sense? It's a sneaky trick. Okay. There are a bunch of hacks in Perlin noise that I think are not worth worrying about, especially today where space is cheap on your hard drive. Like it used to be the one thing that Perlin was very concerned with. Perlin's still alive, by the way. He's a graphics professor at NYU. Was that like somehow storing a big array of basically random numbers seemed like kind of wasteful, right? Because in effect, that's what you need for Perlin noise. Because you understand that you have to decide on those random slopes ahead of rendering. It's not like you can generate them per pixel because then you'll just get noise. Yeah? And so Perlin additionally said, like, well, it would be kind of weird to generate a giant grid of random numbers. So instead he introduced a total hack, which was make a smaller grid of random numbers and then just kind of make sure that the size of that and the size of your grid are co-primed so that you kind of move around it in a way that you don't notice the pattern. Just that way, if you read like the wiki page for Perlin noise, it goes through this data. I think the reality these days is like space is cheap and I would bother with these kinds of hacks. But the more interesting thing is what you can do with it. Hopefully what I've convinced you guys of is that it's not so hard to generate noise that looks like this. Right? You have some grid, you generate a slope out of the grid points, and you just interpolate. Cool? Cool. Okay. So now, what Perlin does, which is really sneaky, it says, I'm going to include noise at a bunch of different scales, right? So this is one scale. You can kind of eyeball it in Perlin noise. And now, maybe I take another octave, like another length scale, and I composite them together, and I allow my artist to control what to do with it. Right? So here, I made the low octave blue and the high octave kind of reddish, and I added them together, and I got the moon, which is pretty cool. And somehow, what Perlin noticed is that by combining relatively few of these things, you can get some really interesting effects. And there's no science here. This is just purely kind of an artistic ideal, but it is one that's been around in graphics for a long time. So I think to make this particular image, what they did is they kind of attenuated the effect of the octave by 1 over its size. And you can see that, right? Because you can see that the most visual effect is this big texture here, but then there's also like a small perturbation, which is the smaller Perlin noise. Right? And in fact, you could do this for more than just 2 scales, and get all kinds of crazy effects. You guys see the basic modeling idea here is once I have random numbers at different scales, I can combine them in funny ways. So what if I took the Perlin noise function and I took its absolute value? What would that look like? It'd be like smooth at most places except where it crosses 0. Right? So it kind of looks like a bunny hop. Like it's smooth, but it has these little sharp edges every once in a while. And what Perlin notices that also is useful for modeling noise. So if you want a really realistic moon, maybe you take some of your noise, you take the absolute value, and that creates some sharp creases in your texture. Right? This sounds goofy and totally heuristic, and that's because it is. But it is by far the most common way that people design procedural texture. Yeah, because the nice thing is, even though this is a very complicated looking texture, algorithmically it's pretty easy, right? And it's creating a high frequency effect. So let's say that I want to model marble. Right? So marble maybe has long strips of dark and then light and then dark and then light. Well, one thing I could do is combine Perlin noise with, I don't know, like some kind of cosine term, right? And what do you get? Well, you get something that looks like marble. And so do you guys see what happened here? So I took the x coordinate of a point, and I took sine of x plus a little bit of noise. Right? So if that noise weren't there, this would just look like larger stripes. But since I've perturbed it now, and the perturbation has something to do with where I am in space, I actually got a pretty interesting texture. Yeah? This is like a really just a magic trick. And so one of the cool things is just like all the neat things that you can do in Perlin noise to get some nice effects. And in fact, there's no reason why this only has to live on a surface. So if I wanted to model a tree, maybe I take some function that looks like cosine in the radial direction and perturb it a little bit, and now I have wood. Yeah? So anyway, this was actually one of the earliest procedural modeling tools in the artistic world, and creates some nice effects. Here's yet another one, like a corona, where let's see, what did they do? They made some function that drops off radially from yellow to red, and they added a phase shift with some turbulence and so on. And it's just amazing the effects that you can get out of this basically hack. But anyway, do you guys see that A, this is procedurally, and B, this is something you can write in just a few lines of code and generate some pretty complex rendering effects. And the nice advantage over this, over say texturing, is in terms of memory, this takes like 0 footprint. Okay? It's just a little tiny piece of code. Yes?
So I've seen like a lot of these textures,
Mm-hmm.
like game engines or graphic things, like do they provide in those graphic design tools, do they provide like a widget where you can actually play with the function?
Absolutely. Yeah, That's exactly how people design Perlin. They'll like actually plot these splines, and the artist has some control over what function they want to apply to it. Yeah. So I think tools like Maya, the Autodesk products, and so have this built in. Yeah. Right. So anyway, the basic ideas here are that shaders take in some ingredients, and those ingredients don't just have to be the texture map. They can also just be actually a random number per pixel, and that can be useful information. And the other takeaway here is that you can layer them as well, right? So for instance, I could have multiple passes over my image and combine them in different ways. And we're going to see that these programmable shaders provide all kinds of cool flexibility that we're going to leverage for basically the rest of 837 to do some pretty cool tricks. Of course, the ones that we talked about today are extremely simple. There are very complex shaders out there, maybe that do really crazy Fresnel, whatever, lighting, and deal with BRDFs and BSSRDFs and all these crazy things. And there can be many, many thousands of lines of code. Typically not the ones in your GPU, because those have to go fast. But if you're in RenderMan and you want to get just the right effect, there's some pretty crazy things. All right, so anyway, that's all today. This is a topic that's close to my heart, so I love talking about this stuff. Frankly, I forget what our next lecture is, but I'll remember before and see you guys then. So in the meantime, finish your. Okay. Turn this thing on.